All right, so this is the 12.4 section on tangent and normal vectors. And again, we're kind of talking about some similar things that we've done before with derivatives of vector-valued functions and finding tangent lines to those things. And this is just a little bit more specific. So, one thing that we're going to talk about here is that now we're going to talk about a unit tangent vector. And again, the word unit implies that it has a length of 1, and the best way to get a length of 1 is to divide a vector by its own magnitude. So the unit tangent vector of t is the derivative of r divided by the magnitude of the derivative of r. So it's r prime over its own magnitude, assuming that the derivative is a non-zero vector. So, pretty easy definition in unit tangent vector is the derivative over its own magnitude. So if we come down here, draw the unit tangent vector to the curve given by r of t equals ti plus t squared j when t equals 1. So I'm going to rewrite r of t in bracket form just because I think it's quicker. So then r prime of t is going to be 1 comma 2t, and r prime of 1, because we wanted it t equals 1, is 1 comma 2. So the unit tangent vector is just r prime over its own magnitude, which is going to be 1, 2, divided by the square root of 1 squared plus 2 squared, which is going to be 1 over radical 5 times 1, 2. Ta-da! And then we said, I put over here, draw r of t and t of 1. So if I'm going to draw r of t can be written as x equals t, y equals t squared. That's parameterizing it, giving it parametric equations instead of the vector-valued function form. So I have x of t, x equals t and y equals t squared, which really means y equals x squared. So the graph of r of t is really the graph of y equals x squared. 1, 2, 3, 4. So r of t is this thing, but it does have direction. As t increases, so does x. So it goes that way. So this is r of t. And then t of 1 is going to be my unit tangent vector at t equals 1. So at t equals 1, I'm at the point 1, 1. And I'm supposed to go up 2, right 1, because 1, 2, your x component is 1, that's your horizontal. Y component is 2. So it's supposed to go up 2, right 1, but only draw about 1 unit in that direction. So that right there would be t of 1. Okay? Find a set of parametric equations for the line tangent to the helix given by that thing, and do that at the point corresponding to t equals pi over 4. All right, fine. So I want the tangent line. Well, a tangent line we talked about before is just going to be x equals y equals and z equals, and then at plus x0, bt plus y0, ct plus z0, where abc comes from r prime. So r prime of pi over 4 is going to give me the a and the b and the c that I need. Okay? So again, your derivative kind of gives you your slope, and instead of slope, it's just coefficients for t. So r prime is what? Negative 2 sine t, 2 cosine t, and 1. R prime of pi over 4 is negative 2 times the sine of pi over 4, which is going to be negative root 2. 2 times the cosine of pi over 4 is just going to be root 2, and 1. And I want the tangent line. Now, I don't need a unit tangent vector this time because it didn't ask for a unit tangent vector. So this would be a tangent vector, and that's going to give me my coefficients. So x is going to be negative root 2 t plus x0. Well, x0 is what I get when I plug pi over 4 into here. So r of pi over 4 is going to be root 2 pi over 4. So root 2t plus radical 2, and then root 2t plus radical 2, and then z equals 1t plus pi over 4. And there's my tangent line to the helix. La-ti-da. Okay, what else do we have here? Now, that was about tangent vectors. There's also something called the principal unit normal vector. And I'm going to tell you right up front, this one gets kind of annoying, but we're going to do a shortcut, so that will make it easier. So if C is a smooth curve represented by a vector-valued function, and T prime, pardon me, is not the zero vector, then something called the principal unit normal vector is T prime over its own magnitude. All right, fine. So I'm going to come over here, and I'm going to say, well, technically there are many vectors perpendicular to T. Therefore, this precise vector is the principal unit normal vector. Now, what do I mean by that? Well, if we look at this diagram, if that's T, technically a perpendicular could be right here, or it could be right there. Or technically, it could even kind of come out this way, and I could have like a slanty right angle in here. That's not what we're talking about. The principal unit normal vector isn't just any normal vector. It always points in the direction in which the curve is turning. It points inward. So, if we look at this picture right here, here's the unit tangent vector, there's the principal unit normal vector, and we are going to go through and calculate it. So, R is 3ti plus 2t squared j, sketch R, t1 and n1, and then calculate n of t and n of 1. All right, fine. So I'm supposed to sketch it first. Easiest way to sketch these is to parameterize it. So x equals 3t, y equals 2t squared, and that means x over 3 equals t, which means y equals 2 times x over 3 squared, which is 2/9 x squared. So if I'm going to sketch that, 2/9 x squared is like a wide parabola here. So there's R. And then t of 1 and n of 1. So when x equals 1, t of 1 looks like this. And n of 1 looks like that. So there's t, and there's n. So visually, again, t is the tangent vector that points in the direction of motion. As t increases, so does x, so I knew that this went in this direction. Ooh, I shouldn't have put that arrow down there. I should have this arrow and that kind of arrow. And so t points in the direction of motion, n points inward. So there I have everything sketched. Now I'm supposed to calculate n of t and n of 1. Okay, fine. So let's do t of 1. We're going to calculate our r primes because I need them to get n. So r was 3t, comma 2t squared. And that makes r prime 3, 4t. So if I want t of 1, I would do r prime of 1 over the magnitude of r prime of 1. So r prime of 1 is going to be 3, 4. The magnitude of 3, 4 is absolutely 5. So I'm going to get 3/5, 4/5. There's t of 1, no big deal. Well, when I want to find n, the problem with n is this. N is defined as t prime divided by the magnitude of t prime. And t of t is 3, 4t divided by the square root of 9 plus 4t squared, which is 3, 4t divided by the square root of 9 plus 16t squared. I now need to take this thing and take its derivative and then find the magnitude of the derivative and divide them. Everybody say, yeah, no, I don't want to do that. Nope, I don't want to do that either. So, for the purposes of our class, I can't promise this if you retake this in college, but for the purposes of our class and in the interest of time, I'm only going to ever ask you about the normal vector when it comes to 2D vector valued functions. The reason why is this. This is in 2 dimensions, right? Which means my tangent vector goes like this. And it points in the direction 3, 4. This is 3, 4 divided by 5. Well, doesn't that really mean that your slope is 4/3? Right? Because this is how much you go up for y, that's how much you go up for x. So doesn't that mean that this slope is 4/3? So if the slope of the tangent line is 4/3, then the slope of the normal line should be perpendicular to that and be -3/4. Which means that in this picture, n of 1, technically I should write n of 1, is going to have an x component of 4 and a y component of 3, and one of them needs to be negated. Now technically negating either of them would get me a normal vector, but since I want the principal unit normal vector, I need to negate the one that would make it point left and up, which means I'd negate this guy. And since it's a principal unit normal vector, I would take 1/5 of that. Okay, so I just did a lot of stuff there, and basically what we did is we did a neat trick. We did a shortcut here. If your tangent vector is 2D, then your normal vector is just the flip-flop of that with one component negated. Now to figure out which component you negate, you do have to graph it. I think that's the best way to tell. But it's basically the idea that you have a negative reciprocal slope, but instead of taking the reciprocal, you just swap the order of the components. All right? So over here, it said calculate n of t and n of 1. So n of 1, I had right here, n of 1 is -3/5, 4/5. And if you wanted n of t, I would just take t of t, which is right here, swap the x and the y, the magnitude would stay the same, and pick one of them to negate, and again I need to go to the left, so I would negate that one. So your unit normal vector is just, or your principal unit normal vector I should say, is just that guy, and then this is your unit tangent vector. All right. And then last but not least, I just wanted to do a quick sketch here. And so just a couple sketches, and then we're all done here. So if I want to sketch t and n at the points below, again, all I'm trying to get at is that t points in the direction of motion and n points inward. So this would be t, this would be t, this would be t, direction of motion, direction of motion. Okay, it's just tangent, and it starts right at that point. So those are all my t's. We'll make that blue. And then all of my n's, my unit normals, have to be perpendicular to the blue but point inward. So that would go like that. This guy, perpendicular but pointing inward, would go like that, and like that. All right. So that's what we have for our principal, unit normal, and tangent vectors for now. I'm going to make another video to wrap up these notes because I'm at 15 minutes already. I will leave you with a dumb joke. Why did the golfer bring 2 pairs of pants? In case he got a hole in one.